In 4.1 and 4.2, we already learned about where extreme values on a function occur and how to use the first derivative to find them. Section 4.3 will take it one extra step to include what's called concavity. So the first question we have to ask is, what is concavity and what does it look like? So concavity is the direction a function is opening. So if it's concave up, means that the function is opening up, and so that would look like this. Concave down means the function is opening down and would look like that. So that's concavity. So then you might ask, all right, well, what is a point of inflection? Because that's the other thing that 4.3 introduces. A point of inflection is a point on a curve, and then just to be clear, a point on the curve where there is a tangent line. So it's a point on a curve where the concavity changes. That's the main thing I want you to get. That's a point of inflection, a point on a curve where the concavity changes. And then also there has to be a tangent line there. So let me show you what that could look like. So you know how those polynomial functions, they kind of go up and down and they change concavity. So in this example here, it's concave down at first, and then right around here, it changes from being concave down to being concave up. So that point right there is what we call a point of inflection, because it went from being concave down to concave up. So it was opening down up until there, and then right there it started opening up. So it's concave up. And right where the concavity changes is called an inflection point. Now, they're not always so obvious like that. Sometimes they're a little bit flatter, like in this example, where the concavity is not as obvious. This is an example where a point of inflection would happen at a horizontal tangent line. So it's flat right here, not as obvious, but the concavity still changes. It was concave down and then it changed to concave up. So we have a horizontal tangent line there. So that also is a point of inflection, just not as obvious. And then there are times when there's no point of inflection at all, like in a parabola, for example, because sometimes a function keeps the same concavity the whole time. So this was concave up the whole time, so there are no inflection points. All right, so we know what concavity is. It's the direction a function's opening. We know what a point of inflection is. That's where the concavity changes. Now we want to see how to find when a function is concave up, down, and then where the points of inflection are. So what we need to know here is that f of x is concave up when the second derivative is positive. When your second derivative is positive, your original function is concave up. F of x is then concave down, you can probably figure this part out, when the second derivative is negative or less than 0. And then the third thing probably follows from there. So f of x, remember, a point of inflection is when concavity changes. So f of x has a point of inflection when the second derivative changes from positive to negative, or vice versa, when it changes sign, because that's when it would go from concave up to concave down. So f of x has a point of inflection when the concavity changes. We had talked about that earlier. So that would be when the second derivative changes from positive to negative and vice versa. So that's when your second derivative is 0. Because in order to go from positive to negative, you have to pass through 0. Or it could also be on occasion when the second derivative is undefined. So we're going to be checking for when the second derivative is either 0 or undefined. So this is really similar to finding max and min, actually. It's just using the second derivative instead of the first derivative. So let's quickly recap how we would do that. To check for max and minimums, you basically have to first check for endpoints, if there are any endpoints. So sometimes that means you have to find the domain of the function. Then you find the derivative of the function, and you find where it's equal to 0 or undefined. So you check basically the zeros or the undefined values of the derivative. So you find those, because that's where the function changes direction. So in other words, a max or min is going to occur either at an endpoint or at a 0 of the derivative or an undefined place of the derivative. That's where your max and mins will occur. To check for increasing and decreasing, you find the derivative. You find where the derivative is 0 or undefined, because as we mentioned before, that would be where a max or a min is. And then you make a sign chart. And what you're doing is you're checking the sign of the derivative. And you're checking it over the interval that's created by these endpoints and these critical points. So that's pretty much what you do to check for max and mins. And notice every time you're checking for, like all the stuff you're checking when it's regarding max and min and increasing and decreasing, you're checking with the first derivative. So max and mins and increasing, decreasing are all related to the first derivative. Concavity, concave up, concave down, points of inflection, that is all entirely related to the second derivative. But you're going to basically be doing the same exact thing. You're going to find the second derivative. You're going to find where the second derivative is 0 or undefined. You're going to make a sign chart, and you're going to check the sign of the second derivative. And you're going to check it over the intervals that are created by the endpoints again. So you use the endpoints, and then you use the points where the second derivative is 0 or undefined. So I can't really squeeze in undefined. So just know that the zeros of f double prime of x, that also includes where f double prime of x is undefined. So notice it's the exact same 3 steps. The only difference is when you're trying to find concavity is you're using the second derivative, instead of the first. So we summarized that the first derivative of a function tells us of increasing and decreasing. The second derivative tells of concavity. Okay, so here's the thing that I need you to really focus in on. The second derivative is the first derivative of the first derivative. Because in order to find f double prime, you take the derivative of f prime. So f double prime is the first derivative of f prime. So that means that if f double prime is positive, if the derivative of f prime is positive, that implies f prime is increasing, because remember, the first derivative tells of increasing and decreasing. If f double prime is negative, then f prime is decreasing, because f double prime is the first derivative of f prime, and the first derivative tells of increasing and decreasing. So now we also have a relationship between f double prime and f prime. But to go even further, if f prime is increasing, that will imply that f is concave up. This is the thing. This is so huge. Why is that? Because if f prime is increasing, that must have meant that its derivative was positive. Because remember, if the first derivative of a function is positive, that function is increasing. So if f prime is increasing, f double prime must be positive. But f double prime, that's the second derivative of f. And the second derivative tells of concavity. So if f prime is increasing, that means f double prime must be positive, because they have the same relationship as a function in its first derivative. Well, if f double prime is positive, that implies that the original function 2 derivatives ago is concave up. Likewise, if f prime is decreasing, that implies that f is concave down for the same reason, because in order for the first derivative to be decreasing, its derivative, the second derivative, must be negative. If the second derivative is negative, that means the original function 2 derivatives ago is concave down. So those are all the relationships. The first derivative tells of increasing, decreasing. The second derivative tells of concavity. And then now we also know that if the first derivative is increasing or decreasing, that can help us tell if the original function is concave up or concave down. So let's go ahead and do some practice from the book. So this example I'm about to do is to help you out with numbers 3 through 6 in the bookwork. This is asking us to use the graph of the derivative to estimate, meaning the answer doesn't have to be exact. We're just going to estimate where the function, the original function, is increasing. That means going up, decreasing, going down, and then where there are any local extreme values. Well, I know that f is going to be increasing when its derivative is positive. So I come over to the graph and I look to see where the graph, where the derivative, which is what this is positive. That means above the x-axis. So that's between -2 and 0, and then between 0 and 2. Then the function is going to be decreasing when its derivative is negative. So I look on the graph. That would be when the graph is below the x-axis. So that's to the left of -2 and then to the right of 2. And they aren't really clear here if the graph stops or keeps going. So I'm going to just assume that it keeps going. And I'm going to say that it's decreasing basically all the way to the left of -2. So between -infinity and -2, and then all the way to the right of 2. So between 2 and infinity. Then f is going to have a local max or min when it changed direction, or where the derivative is equal to 0. So that is at -2, 0, and 2. But it's specifically when the function changed direction. That's really where you have a max or a min, is where the function changed direction, where the derivative changed sign. So actually, I'm going to erase that and say where f prime of x changes sign. So then that rules out the 0. That is not going to be a max or min because the derivative stayed positive to the left and positive to the right. That means the function was increasing all the way from -2 to 2, so there's no extreme value at 0. But there is going to be an extreme value at -2 and at 2, because that is where the derivative changed sign. At -2 it went from negative to positive, and then at +2 it went from positive to negative. For example 2, it wants us to use the graph of the function, not the derivative. So this is the function, to estimate where the following, that's f prime and f double prime, are 0, positive, and negative. Okay, so I know that f prime is going to be 0 when the original function changed direction. So f prime equals 0 when f changes direction. But also when you have a horizontal tangent line is another place where your slope is going to be 0. So I can see that that is going to happen right here, and right there. So I'll put or when tangent line is horizontal. Okay, so that happens at, looks like about negative 1.2, 0, and positive 1.2. So that would be where it's 0. Then I know that f prime is going to be positive when f is increasing. That means when f is going up from left to right. So I can see I'm going to be going up from left to right between negative 1.2 and 0. The function's going up. I'm also going to be going up between positive 1.2 and infinity, because to the right of this point here, the function's going up. So that will be when f prime is positive, when the function is increasing. So f prime is going to be negative when f is decreasing. So then I look to see when the function's going down. That's when its derivative is negative. So it's going down from negative infinity to negative 1.2. And then between 0 and positive 1.2. So that was part A. Then for part B, the second derivative will be 0 when the concavity changes. So f double prime is 0 at the points of inflection, or where the concavity changes. So that looks like it's right about here, because the function starts off concave up, and it's concave up until right about here-ish. This is where we're going to estimate a little bit. And then it begins to be concave down until right about there-ish. So that looks like it's right about, I don't know, negative 0.5 and positive 0.5 is roughly when it changes concavity. So it was concave up till right about there. And then it changed to be concave down, opening down till right about there. And then it changed to being concave up. So those two places are at approximately negative 0.5 and positive 0.5. Then the second derivative is positive when the original function is concave up. So it's going to be concave up from negative infinity to that first inflection point, negative 0.5, and also from 0.5 to infinity. So the right side and the left side were basically both concave up. And then it's going to be concave down when it's opening down, and that was between the two inflection points. So it's going to be concave down between negative 0.5 and 0.5. So these examples we're using graphs. The next example we're going to use what's called analytic methods to find all these different things. The steps I'm going to do, or I'm going to show you in example 3, are going to help you with numbers 7 through 27. There's going to be easier ones like this, but there's also going to be harder ones that I'm going to show you in the next video. I'm asked to find 6 things: where it's increasing, decreasing, where it's concave up, concave down, where the local extreme values are, and where the inflection points are. So there's 2 points to this, because to find where it's increasing and decreasing, I have to use the first derivative. And then the first derivative will also help me find the extreme values. But to find where it's concave up, concave down, the inflection points, I have to use the second derivative. And I can't really, there's no shortcut. You have to basically do 2 different problems. Okay? So to do parts A, B, and E, I'm going to do steps 1 through 3 that we had done back in 4.2. So this is for parts A, B, and E. I'm going to find the first derivative of this function here. So that is basically negative 4x cubed plus 12x squared minus 4. There's my first derivative. Then I'm going to find where that is equal to 0 or where it's undefined. Oops. Well, this is not going to be undefined because it's just a polynomial. So I'm going to find where it equals 0. But I have a bit of a situation. This cannot be factored. So I'm going to let you go ahead and use your calculator here. The way one would do that is you would just enter that equation into your calculator. And I always like to hit zoom 6 because I never remember what my original window is. Okay, so there's 3 places where my derivative equals 0. And I'm just going to go ahead and find those places by doing second trace, which is calc, 0. And I'm going to have to do this 3 times. And I want you to follow along with me because I want to show you how to store the answers on your calculator. So let's just start on the left. I'm just going to go over to the left, hit enter, go to the right, hit enter. Then it asks me to guess, so I'll hit enter a 3rd time. And then there's my first 0. Okay, don't clear anything. Just hit second quit from here. I'm going to have you store that answer so you can refer back to it later. And I'm going to restore it as a letter. So I'm going to hit alpha A. So now, anytime I hit alpha A, it'll give me that number. And then now maybe I'll write it on my paper as well. So my first place where the derivative is 0 was at negative 0.532. That's the first place. Now I'm going to go ahead and find the second and the third. So I'll go back to the graph. I'll hit second calc 0. Go to the left of the second root, then to the right of the second root, enter, and then before I do anything, don't clear anything, just second quit, I'll store this one as alpha B. And so that's my second root. Alright, then I'm going to find the third one. Second calc 0, go to the left of that, whoops, went too far, and then to the right, get that third root, second quit, store it as alpha C. And it was 2.879. Okay, then step 3 is you create your sign chart. And you break up the interval over these critical points. And there are no endpoints because the domain is all real numbers. So I should probably write that at the beginning. The domain is all real numbers, so that implies that there are no endpoints. So in other words, I'm going to start my sign chart all the way at negative infinity. And I'll just go from left to right. So I'll have it stop at negative 0.532. Then I'll have it go from negative 0.532 to 0.653. Then I'll have it go from 0.653 to 2.879. And then lastly from 2.879 all the way to positive infinity because again there are no endpoints. And what we're doing here is we're checking the sign of the first derivative. We're checking the sign of f prime because I want to see where my function is increasing and decreasing, and that's where the first derivative is positive and the first derivative is negative. So I'm going to check a number to the left of negative 0.5. An easy one would be negative 1. So I'll plug negative 1 into my derivative. This would become positive, that would become positive, and these numbers would be larger than negative 4, so that's going to be a positive. So then that means my function is increasing because my first derivative is positive. Now I have to pick a number between these two. That's not going to be as easy. I guess that would be, oh actually sorry, this is positive. That will be easy because I can plug in 0 because this is a positive, that's a negative. So I can plug in 0 and then I get negative 4, so that's negative, so the function is decreasing. Here I have to pick a number between 0.653 and 2.879, so a number like 1 would be easy. So that would be negative 4 plus 12 minus 4, that would be a positive number. The function would be increasing there. And then here I can pick any number larger than 2.879. So sometimes when you have to pick a larger number, an easy one to choose would be the number 10. So you could test the number 10, because this would just become, it would be negative 4,000, because it's just a negative 4 with 3 zeros, plus 1,200, because it's just a 12 with 2 zeros, minus 4. So you can see right away that would end up being negative. So sometimes that's an easy one to test. All right, now I have enough information to answer parts A, B, and E. For part A, the function's increasing wherever the first derivative is positive. So that would be from negative infinity to negative 0.532, and then from 0.653 to 2.879. That's where the function's increasing. Part B, it's decreasing wherever the first derivative is negative. So that's between negative 0.532 and 0.653, and also between 2.879 and infinity. Then for part E, because this has no endpoint, this is going to go forever that way and going to go forever that way. So it went up, stopped, and then went down. This is a max, a local max. Then it went down, stopped, and went back up. That's a local min. So this is a min, that's a max. And then it went up, stopped, and went down, so that's a max. And one of these is absolute, one is local. We'll figure it out in a sec. But these two are maxes, and that one's a min. We can tell because of the direction the function was going in. Okay? So it looked like the function did something like this. Up, went down, stopped, went up, went down, stopped. I just don't know which one of these is higher. So what we'll do is we'll plug these values back into the original. So we have a max when x is negative 0.532, and we need to find out what the max equals. Here's where the storing of the values comes in super handy. So I'm just going to teach you some little calculator tricks here. So go back to your calculator and enter in the original function. Go ahead and put it in for y2. So the original function was negative x to the fourth plus 4x to the third minus 4x plus 1. And then just quit back to your main screen. Let's clear all that out. So I want to figure out what the value of the original function was, and the original function is y2, and I want to figure out what that value was at negative 0.532, which I had stored earlier as a. So I'm going to do alpha a. I'm just going to plug it in there. And then it saves me the time and hassle of having to plug in that complicated decimal into this original equation. The calculator does it all for you. So the value of y at negative 0.532 is 2.446. Then I have a minimum when x is 0.653. So I'm going to figure out what the y value was there, because I have to find what the minimum is. So I go to vars, y vars, function, and I'm going to go to y2 because I'm plugging it into the original. And that was my second value that I'd stored, so that's negative 0.68. That's my minimum. And then I have my other max at x equals right here, 2.879. And so that is going to equal, so that's my absolute max right there. Local max, local min, absolute max at 16.234. And the reason why this is a local min is because the function goes down forever on either side. And so this is not going to be the lowest value overall, just over that neighborhood. In fact, maybe we can take a look real quick at the graph since I put it in there. Let me take off the derivative. You can see, yeah, so it goes up, down, and it just went up a lot further the second time, so that was your absolute max. So local max, local min, absolute max. All right, so we basically did half of this question. Now we have to go and answer parts C, D, and F. We have to find the concavity. So I'm going to do the same 3 steps, but with the second derivative. So I'm going to find f double prime. which is the derivative of the derivative. So that's negative 12x squared plus 24x. I'm going to find when the second derivative equals 0. So that would be when negative 12x, I'll factor that out. So I have x minus 2 equals 0. So that would be when x is 0 or 2. And then I'm going to set up a sign chart over those values now. So I'm going to go from negative infinity to 0, 0 to 2, 2 to infinity. And I'm checking the sign now of the second derivative, because that will tell me where the function is concave up or concave down. That will tell me about the concavity of the function. So if between negative infinity and 0, I could maybe choose like negative 1. So then I'd have negative 12 minus 24. Clearly that's negative. So that means my original function is concave down on that interval. Then between 0 and 2, I could pick positive 1. So I'd have negative 12 plus 24. That would be clearly positive. So my function then, my original function is concave up. Then greater than 2, I can maybe pick like 10, like we talked about before. So I'd have negative 1200 plus 240. Well, that's obviously going to be negative, so my function is concave down on that interval. So now I'm able to answer parts C, D, and F. So for part C, wanted to know where it's concave up. So that would be when the second derivative is positive, so that was between 0 and 2. Part D wanted to know when it's concave down. That's when the second derivative is negative. So that was from negative infinity to 0, and then from 2 to infinity. And then, whoops, sorry, part F. Last but not least, I need to find my points of inflection. That's where the concavity changes. So that was at when x is 0 and when x is 2. So I need to figure out what the y values are there. So I'm going to come back to my calculator and do y2 evaluated at 0 and then y2 evaluated at 2. So that was 0, 1 was 1 point of inflection, and then (2, 9) was my second point of inflection. So you can see how involved these problems are, because they basically are two problems wrapped into one. When you're asked to find increasing, decreasing, and extreme values, you do the first derivative. When you're asked to find if it's concave up, down, and then inflection points, you use the second derivative, but the process is the exact same. So we're going to try out a couple of these in class, and I'll see you there.